What we're going to do in this lecture is to give a proof of the transfinite recursion theorem on ordinals, and then see how to apply that for definitions of ordinal arithmetic. And we'll end up proving some basic properties of that arithmetic. So last time I introduced the recursion theorem and went through the clauses that you could use to have a second form of the recursion theorem, where we do definitions by cases. This will be the form of the theorem that we'll use most often, because we'll define something that happens at 0, something that happens at successor ordinals, and then something different that happens at limit ordinals. But first we'll do the recursion theorem's proof in its first and more complete form. So to remind us what that looks like, this is theorem 335. The data we're given, in fact, is just the one function, capital F, from sets to sets. And there exists a unique function h, which is going to send the ordinals into sets. And the idea is that h of alpha will depend upon the previous values of h betas for beta less than alpha. We'll line all those values up and apply f, and that'll tell us what the next thing is. That's how it's going to work. And we saw, I sketched what happens in the first few stages there for h0, h1, and so forth. And then what we're going to do is see how this works, all told, for the later stages. Right, so let's go through that proof. Now I'm going to stick pretty much verbatim to what's in the printed notes here, but I'm just going to talk our way through it. That's the idea. So this is page 33 on the notes. Now, I've deliberately set it out so that it looks as much like the proof of the recursion theorem on the natural numbers. Right? So, of course, this was done intentionally. And if you recall there, the proof there, you put together the function h by piecing it from smaller approximations, piecing it together from smaller approximations. So we do the same thing here. What we're going to do is, of course, define approximation in this new setting where the approximating functions can have transfinite domains. So again, the idea is we piece together. So our h using approximations. And this time we're going to say something is a delta approximation. This will correspond to a k approximation in the sense of the approximation functions we used for the recursion theorem on omega. And the delta is going to be the length of the domain of the function. Delta approximation is u. And to be a delta approximation, u had better be a function, and its domain is delta. And it's going to look like a piece of a piece of h. So for all alpha less than delta, u of alpha is going to be f of u restricted to alpha. So this corresponds entirely with the h that we're going to get. We want h of alpha to be f of h restricted to alpha. So the approximation satisfies the clauses 1 and 2 here. Well, clause 2 is the important one here. The approximation satisfies clause 2 all the way up through its domain. So we saw u of 0 is just going to be f of 0, or f of the empty set, which is whatever it was. So again, a 1 approximation is just the ordered pair 0, f of 0. Right? It's a 1 approximation because its domain is just the set containing 0. Here's the domain of the function. Let's call this u0 here. Domain of this is 1, right, which corresponds to here. So actually in the notes, I've called this 1 approximation V. So let me stick with the notation of the notes. So that's one thing to observe. Second thing here to observe. If U is a delta approximation, I think of U as, okay, so it's some kind of function up here to delta. So it's a delta sequence of sets, not ordinals necessarily. Right? But if I cut it off at some earlier stage, U restricted to gamma is a good approximation. It's going to satisfy these same clauses, of course. I've just taken less of it. So it's a gamma approximation here. So this is true for any, well, gamma less than or equal to delta. And the third point is that just as we did for k-long approximations, I can always extend an approximation one more just by invoking the function f up here. So if U is a delta approximation, then all I have to do to make it a delta plus 1 approximation is to add on the necessary ordered pair. So then this here is a delta plus 1 approximation. Indeed, it's the only delta plus 1 approximation extending U. And we'll argue later that it's the only delta plus 1 approximation, full stop. So any approximation can be extended one more step by just following the rule one more step. And we're going to let B be the class of approximations. And if there's an approximation for every ordinal delta, this will be a proper class, because there's a proper class of deltas here. And now the layout is a little bit like what we did before. Well, a lot like what we did before. We first said if U is a k approximation and k prime was smaller than k, then the restriction would be a k prime approximation, and they would agree on their domains. So if U is a delta approximation and V is any gamma approximation, and let's suppose delta is less than or equal to gamma here, then actually that just says U is an initial segment of V. So the picture would be, here is U, going up to gamma, and here's, sorry, delta, and here would be V going up to gamma. U is just an initial segment of V. So this equals this. Right? And the reason is just as before. We look for the least point of difference if they were to be different. So as before, least point of disagreement between U and V restricted to delta. The claim says there aren't any, but let's suppose there is one. So if there were one, let Tor be its least, be the least such. Now I can say least such because I know that the ordinals are well ordered. In particular, the ordinals below delta are well ordered. So if there's going to be a point where they're different, there's going to be a least point where they're different. So this will give us our contradiction. Because Tor is the least such, below Tor, they agree. Right? So here would be U restricted to Tor. So they agree up to Tor, but somehow at Tor they're supposed to differ. So here they agree. But they're approximations. So they must satisfy this clause here. U of Tor is going to have to be f of U restricted to Tor, and likewise for V. But this is f of V restricted to Tor, and this by definition of V being an approximation is V of Tor. So they don't differ after all. They're the same thing. Contradiction. So there's no such Tor. And one is proven. Right? V cut down to the length of U agrees with U. And at this point in the proof of recursion on the natural numbers, I said, well, if there was a function h, it would be unique because of this argument. And that's exactly the same here. So the second clause here would be uniqueness of h. So if h exists, it's unique. So I would say just as above. If h and h prime were two such, look for the least Tor where they differ. And get a contradiction in the same way. So there's nothing else to actually, nothing new. There's no new idea needed. And again, the substance of the matter is existence of h. Sorry, it's not quite how I've set it out. That's going to be 4. We do some little something else first. If I take a limit lambda, and for all alpha less than lambda, I've got U alpha approximations. Then, so if then, I can just take the union of these U alphas. This is a lambda approximation. So the picture here is, here's lambda. And here I've got all of these approximations. By appealing to clause 1, which I just proved, these all extend each other. I cut down one to the domain of another and they agree. So these are little small functions that all extend each other, domain extending. So what we do is take the union of these functions and we piece them all together and we get U lambda. So I just think of U lambda as just being built up, if I like, in these stages, by the stages of recursion. So that's all that 3 says. Right? And it's kind of fairly clear from the picture. Right? But we can say a little bit about that here. So the union here as I've just said, is union of an increasing sequence of sets. Increasing sequence of sets, right? Meaning if alpha is less than beta is less than lambda, then U alpha is a subset of U beta. These are all functions. And the union of the whole lot is a function then. And its domain is lambda. U alpha's got domain alpha, but the union of the whole lot has domain lambda here. So this is a lambda approximation. So 3 is just saying I can take a union of a chain of some limit ordinal length of approximations, union it up, and I'll get an approximation of the appropriate length here. So now we get existence. Existence of H. And we do what we did before. I'll take the big union of that B. What was B? B was the class of all possible approximations. We've just shown that they all agree on their domains. Just as I unioned up a lambda sequence of approximations, alpha approximations for alpha less than lambda, to to get a lambda approximation, I'll just take the union of all possible delta approximations for all delta. So I let H be the big union of B. So just as we showed for the recursion theorem on omega, first of all, H is a function, basically because it's put together from functions which all agree with each other. And so I'll say no more about that. As before. By before, I mean as in the recursion theorem on omega. And the point is that H has got domain all the ordinals. That's what we want. And we could do more or less the same argument as before, except now, of course, we've got another case to consider because our ordinals come in three flavors. There's not just 0 and successor k's, k plus 1s. We have these limit ordinals as well. Okay, so let's suppose C is the class of ordinals delta, so there's no delta approximations. And hopefully C is empty. Suppose C was a non-empty class. By the principle of transfinite induction, it would have a least element. Which I've called psi. By principle of transfinite induction, this is lemma 324. So there's a least point where things go wrong, right? If C is non-empty. There's some psi such that there is no psi approximation. And we will, sorry, in the notes I've said zeta. So I'll stick with that notation. And we just reason that that's a contradiction. So zeta is bigger than 0 because we know there is a 0. Well, it's bigger than 1 because we showed above there is a 1 approximation. So as we saw above, there's a 1 approximation. So 1 is not in C. But by the reasoning that we did here on 3, zeta can't be a limit ordinal. If zeta was a limit like this, it would mean for all things smaller than zeta, we'd have these smaller approximations that I could put together to form a zeta approximation. So 3 has already established for us, and that's why we did this a little bit early, that if this is a limit, there is going to be zeta approximations. So 3 above showed that zeta is not a limit. So it must be a successor of something, and that'll give us our contradiction. So if zeta is mu plus 1, by the leastness of zeta, we have a mu approximation, V, say. But we also saw above how to extend an approximation one more stage. So we also saw above how to extend an approximation one more stage. All I have to do is just set U to be V, and I just add on that extra ordered pair, mu f of V. And this then is a mu plus 1 or zeta approximation. So there is such an approximation. So zeta is not in C. So this is a contradiction because zeta was assumed least in C. So C is empty. So C is empty, and this means every ordinal is in the domain of H because it's in the domain of some approximation. Every ordinal zeta is in the domain of H because zeta is in the domain of U, where U is a zeta plus 1 approximation. And U is in B. So every ordinal gets catered for here. So H exists. So what we have is a kind of abstract recursion theorem here. More or less everything has been, anything that we're going to see will be related to this. And so every function on ordinals that we see are going to be somehow related to this one here.